Lesson 4-4, Prime Factorization. And in this lesson, you will learn to identify prime and composite numbers and to write the prime factorization of composite numbers. Okay, why is it important? You can use prime factorization to help you determine a box's dimensions when you know its volume. Okay, but let's take a look at this activity first. As you've learned in 4-3, drawing a diagram can be very helpful as you solve problems. The grid at the right shows one way of drawing a rectangle consisting of 10 squares. Okay, use the grid paper to draw as many different rectangular arrangements of 1, 2, 3, 4, 5, 6, 7, 8, and 9 and 10 squares as possible. Okay, so let's take a look at number 1 and see how many possible combinations there are. It's very obvious. Okay, so if you get example number 1, all you need to do is get one of these things. Okay, and there is one possible combination. This is the only possible combination right there. Oh, let me lock that so it won't move on us. There you go. Okay, so if you get that one, that's your only possible combination since it's 1. Okay, so that is 1 right there. Okay, we'll put the 1 right there. Okay, and if we get 2, okay, there are 2 ways to do number 2. This is one way. Okay, and another way would be, let's clone this, 2 going sideways. There you go. So that's 2 right there. I'll put the number 2 right there. Okay, and we get 3. Okay, so we get this again. And if you notice on 3, there are also 2 possible combinations to make 3 squares. Okay, that's one possible combination. And another possible combination is lengthwise. Okay, and that's our number 3. Okay, for 4, let's see how many possible combinations there are. Okay, so you have 4 squares right there. So that's one possible combination. Okay, another possible combination would be 1 by 4. Something like this, I think. There you go. Okay, so 1 by 4. Okay, another possible combination would be to make this horizontal. Okay, right there. So you can see in 4 there are 3 possible combinations. And let's take a look at 5. Okay, that's still 6. So there is, again, I'm thinking there's only 1. Actually 2 possible ways of writing or creating a rectangle with 5 squares. One is to let it stand up vertically, and the other one is to let it lie horizontally. So I have 2 possible combinations to make 5 squares in a rectangle. And the number 6, okay, so that's 6 squares. We can do actually a 2 by 3 square. So 2 by 3 square is one possible combination. Another possible combination would be to get that 2 by 3 square and let it stand up. Again, we still have 6 squares there. Another possible combination would be to, okay, get a square. Let it stand up so it's easier for me to maneuver. And make 6. Oopsie. 6. Oh, what happened there? 1, 2, 3, 4, 5, 6. That should be there. Another possible combination is get that lying down there. So in 6, there are 6 possible combinations to make 6 squares in a rectangle. Okay, 7 is going to be just 2. Okay, and that's going to be, let me get that 7. We're rounding out of space, but we'll try our best here. Right here, so we get 7. 1, 2, 1, 2, 3, 4, 5, 6. We'll get one more right here. Right here. That's a 7. Right there. And then we get the same 1. And we simply lie it down right here. And that's going to be your 7. Okay. It's getting tight. Okay. And number 8. Okay. We'll do 8 last probably. And then you just have to take my word for 9 and 10. Okay. For 8, we get our square. Bring it here. And we have 8 square. We need to create 8 squares out of that. So you have, we can do a 2 by 4 square. Okay. We can do 4 by 2 square right here. We can even do a 1 by 8 square. 1, 2, 3, 4, 5, 6, 7, 8. Okay, that works. Right here, we're not doing that. Right over all the way. Oops. Okay. One way, and then we can also do. You can let it lie down. Something like this. 8 squares. Okay. Right there. So you have 4 possible combinations. Okay. And you get the point. In number 9, you will have 3 possible combinations. And in number 10, there are 4 possible combinations. So this is your 10 right here. You can make this lie down. Okay. Okay, so making this lie down right here. I'm going to get that 10. Right there. Now where's my 10? Okay. What I can do is make this lie down right this way. Still 2 by 10 right here. Okay. There you go. Or it can be one line of 10 horizontal. Okay. So there are 4 possible combinations for 10 to make a rectangle. So this will have 4 possible combinations, and you just have to take my word for 9. This has 3 possible combinations that you can make a square. So in 1 you have 1 possible combination, 2 you have 2, 4 you have 3, 3 you have 2, okay, 5 you have 2, 6 you have 4, 7, 2, 8, 4. Okay, what does this tell us? Okay, let's answer the questions first. Which numbers of squares could only be arranged in either one row or one column? We can answer that right now. It's going to be 1, 2, 3, 5, and 7. Okay, they can only be arranged by either one row or one column. Which squares could be arranged in either in a way other than one row or one column? We have a bunch of them. We have 4, 6, 8, 9, and 10. Okay, finally, letter C. Choose one of the numbers that could only be arranged in one row or one column. Write as many multiplication sentences with the number as a product and two whole numbers as factors as you can. Okay, so what it's saying is this: if I choose, okay, the number 2, which can only be arranged in one row or one column, okay, how many multiplication sentences with the number as a product, okay, and two whole number factors can we do? So in number 2, what are only the possible ways you can multiply that to get a product of 2? So you have 2 equals 1 times 2, and 2 equals 2 times 1. Those are the only two ways. And that goes the same with 3, because 3 can only be done by 1 times 3, or it can be 3 times 1. That's the same with 5, that's the same with 7, okay, and that's the same with, yeah, that's it, below 10, okay? And if you notice, we did not do 1. Why? Because 1 can only be done as 1 times 1, okay? What is the rule then? The rule is, okay, there are only two ways, n times 1 equals n, and 1 times n, where n represents the number. Okay, so knowing what we know in creating these little rectangles, we can learn the concept. So in the activity, the numbers of squares that can be arranged in only one row or one column are called prime numbers. Okay, definition of a prime number, write this down. You are going to carry this on all the way to high school. Prime number is a number greater than 1 that has exactly two factors, 1 and itself. Okay, so again, the reason why we do not include 1, because a prime number should be greater than 1 and has exactly two factors, and 1 has only one factor. So it has exactly two factors, 1 and itself. Okay, numbers like 4, 6, 8, and 9 and 10 that can be arranged in rectangles other than one row or one column are called composite numbers. So definition of a composite number, write this down, is a whole number greater than 1 that is more than two factors. Composite number can always be expressed as the product of two or more primes. Okay, so a few things here that you need to remember. Composite number has more than two factors. Also, composite number can always be expressed as a product of two or more prime numbers. Okay, what else? Okay, we know that the numbers 0 and 1 are considered neither prime nor composite because they do not follow the definition. 0 has only one factor, has more than one factor. Okay, and 1, okay, has only one factor. So when you look at the definition of a prime number, and it says also in the composite number, since 0 has more than one factor, you can do 0 times 1, 0 times 2, 0 times 3, 0 times 4, 0 times 100, okay, those are all factors of 0. Why is it not a composite number? Because it follows the second rule, because in a composite number, it can be, always be expressed as a product of two or more primes, and that does not fall into 0. And 1 has only one factor, so it's neither prime nor is it composite. What else do we have to know? That every number is a factor of 0, since any numbers multiplied by 0 is 0. We know that. The number 1 has only one factor, which is itself, and every whole number greater than 1 is either prime or composite. So any number, any whole number greater than 1 is either prime or composite. Okay, definitions out of the way. Sometimes a number can be factored in several ways. 3 different ways to find all of the prime factors of 24 using diagrams called factor trees are shown below. So if we use 24 and we use a factor tree, these are all the possible ways we can find factors of 24. First 24 is 2 times 12. Okay, and we also know that 2, since it's prime, we simply bring down the 2, because it's the only two factors left would be 1 and 2, and we don't write 1 in the factor tree. And give me 2 factors of 12. In this case, 3 and 4 was given. Okay, so we still bring down the 2 here, bring down the 3 because that's already prime. Okay, but 4 is not, so give me 2 factors of 4 that's left. That would be 2 times 2. Okay, all of them are now prime. we stop the factor tree. Okay, let's look at another factor tree for 24. Let's do 3 times 8. Okay, we know that 4 or 3 is already prime, so we just bring it down. Okay, with 8, we can still find factors of 8. That is not 1. So you have 2 times 4. Okay, continue to bring down that 3 and that 2 because 2. Okay, only factor left for 2 is 1, and we don't write 1 in our factor tree. Okay, and 4 has factors 2 and 2. Since all of them now are prime, 3, 2, 2, and 2, we stop our factor tree. And let's do one more factor tree for 24, and that is 4 times 6, okay, equals 24. Okay, we can factor 4 some more, so we do 2 times 2, and 6 as 2 times 3. All of them are prime. We stop our factor trees. The factors are different in order, but the result, if you notice, will always be the same. The order in which you factor is not important. Again, it is not important. The factoring process ends when all the factors are prime, and that's exactly what we just did. When a positive integer other than 1 is expressed as a product of factors that are all prime, the expression is called prime factorization. And if you notice, if you follow that definition, this is the prime factorization of 24. They're all the same. So the prime factorization of 24 is actually 2 times 2 times 2 times 3. And if you want to use exponents, the prime factorization of 24 would be 2 to the third power times 3. Okay? Okay, moving on. Let's go to example number 1. Use a factor tree to factor 64 completely. Begin with any two whole number factors of 64. Okay? Okay, let's look at 8 times 8, which are any two whole numbers of 64. And we know that 8 is not prime, so we continue factoring. So that becomes a 4, and that becomes a 2. Okay? And then we know that 2 is prime, so we simply bring down the 2 right there. So after we know that 2 is prime, we simply bring that down. But we know that 4 is not prime, so we continue factoring. 2 times 2. End up with 2 times 2 times 2. Okay? And 2 is prime, we stop factoring, and we do the same for the other 8. Okay? So we now have 1, 2, 3, 4, 5, 6. Okay? 2's. So 2 being used as a factor 6 times. So 64's prime factorization is 2 times 2 times 2 times 2 times 2 times 2, or 2 to the 6th power. Okay? So the prime factorization of 64 is 2 to the 6th power. Again, we stop prime factorization. Our prime factorization is complete when all the factors are prime. Let's take a look at number 2. Okay? In number 2, the prime factorization of a negative integer other than -1 contains a factor of -1, and the rest of the factors are prime. And if you notice, look at the direction from number 2 and compare it to the direction for number 1. Use the factor tree to factor 64 completely. Okay? In 64, we are looking for the, we can also say that we can also indicate, find, okay, the prime factorization of 64. So this direction can be said for number 1. Find the prime factorization of 64. Why? Because a prime number is greater than 1, meaning it has to be positive. Okay? In example number 2, you cannot use that direction. Why? Because you have -72. And that's the reason why it's saying use a factor tree to factor -72 completely. Okay? Because a number less than 0 cannot be considered, okay, a prime number. So the prime factorization of a negative integer other than -1 contains a factor of -1, and the rest of the factors are prime. Okay? So let's factor negative 72. Let's use a factor tree to factor negative 72 completely. Okay, so let's start with, let's make negative 72 positive by doing negative 1 times 72. Remember, negative 1 cannot be a prime number or composite number because it's a negative. Okay, so we get that negative out of the way. We can now factor 72. So we simply bring down the 1, negative 1 every single time. Any two factors of 72 will do. In this case, we use 8 and 9. And we know for a fact that 8 is not a prime number, 9 is not a prime number, so we continue factoring. And we simply bring down the negative 1 as well. Okay, so any two factors of 8 will do. In this case, we use 2 and 4. Okay, two factors of 1 and 9, there are only 2 left, 3 and 3. Again, we are not using 1 as a factor. Okay, so looking at our problem right here, we bring down negative 1 right away. We know that 2 is prime, so bring that down. 2 is not prime, so we continue factoring 2. Two factors of 4, are 2 and 2. Both of them are prime. We stop. So this is prime, that is prime, that is prime. We stop there. Both 3's are prime, so we simply bring them down. Okay, so if we completely factor negative 172, oh, I forgot to write all the reasons for each step. Negative, the integer may be expressed as part of negative 1. We know that. Okay, we know that, and okay, we factored 4 in this case. So you are finished. Okay, factoring when all of the factors other than negative 1 are prime. So the factorization of negative 2 is negative 1 times 2 times 2 times 2 times 3 times 3. You can write this as a product as negative 1 times 2 cubed times 3 squared. Okay? Okay, notice that it did not call it the prime factorization of negative 72 because negative 1 is not prime. Okay? So a little trick here. On the next part, you can also use a strategy called the cake method. I like to call it the drop-down method. Okay. If you want to follow this is the book's example of the cake method. But what I'm going to show you is the drop-down method to find the prime factorization. They're basically the same thing. I'd rather prefer the drop-down than the cake method, but they're the same. The directions are the same. The method is the same. The steps are the same. The cake method uses division to find factors. For example, the prime factorization of 210 is shown below. The first step is to begin with the smallest prime factor, and let's find the smallest prime factor of 210, which is obviously 2. Okay, because 2 goes into an even number. Okay, and you write an angle there going down. Okay, and 210 divided by 2 is 105. Okay, the next step after that, then divide the quotient by the smallest possible prime factor. What it's saying is this. Okay, what's the smallest prime factor that go into 105? And this is where your divisibility rules come in. Okay, you have 1 plus 0 plus 5 is 6. That means this is divisible by 3, which is also a prime number. So 105 divided by 3 will give you 35. Okay, again, last step, repeat until the quotient is prime. So we know that 35 is not prime. How do we know this is not prime? Because this is divisible by 5, and once the divisibility rules apply to a number, it is not prime because it has more than it has more than 2 factors. So the divisibility rule applied to 35, okay, which means that this is divisible by 5. So 35 divided by 5 will give you 7. And we know for a fact that 7 is a prime number. So therefore, the prime factorization of 210 is, okay, 2 times 3 times 5 times 7. And you can use a tree diagram to check your result. Okay, last example. Not yet. 2 more examples. Prime numbers are the key to coding and decoding information using Rivest-Shamir's Adelman crypto algorithm. Two prime numbers P and Q are chosen, and the key to code is n equals PQ. Find P and Q if n equals 1073. Okay, let's do this problem. First and foremost, the greater the prime numbers, the more difficult it is to break this particular code. Okay, some possibilities that we can do is that some possibilities can be eliminated by using divisibility rules that we learned in the last lesson. Okay, or not in the last lesson, 4-1. We know that 1073 is not divisible by 2, since the ones digit is not divisible by 2, or simply saying it's not even. Okay, it is not divisible by 3 because when you add up the digits, it's 11, and it's not divisible by 3. Again, it's also not divisible by 5 since the ones digit is 3, not 0 or 5. Okay, then after we know it's not divisible by 2, 3, and 5, let's use a calculator. Okay, and check and guess and check. Okay, to continue checking for primes. So you have now 1073 divided by x. Okay, and if x equals 7, okay, we know that it will not be a factor of 1073 because it will contain decimals. It's the same thing with 97, with 11. Okay, and we go down the line. 13 would also be a no. Okay, we'll have decimals. 17 will also be a no, decimals. 19 a no, again decimals. 23 a no, decimals. But look at the number 29. If you divide 1073 by 29, you get 37. So this is a yes. So therefore, using guess and check, okay, we know that if n equals 1073, then P and Q are 29 and 37. Okay, and that's how you apply prime numbers in this type of a problem. Obviously, there's another way of solving this problem, but we'll not go into that simply because that's not our lesson yet. Okay, let's do our connection to algebra. Last example, a monomial can also be written as factored form. In factored form as a product of prime numbers, -1, and variables with no exponent greater than 1. Okay, so let's look at example number 4. Factor each monomial completely. Again, we want to find the prime factors of 28x squared y. So first, we get the prime factors of 28. The two factors of 28 are 2 and 14. We know that 2 is prime. We bring that down. 14 is not, so we continue factoring 14 until we get 2 times 7. If you notice, these are all prime numbers, so we stop, and we simply expand x times x squared to be x times x, and bring down the y. Okay, and this is how we factor, okay, 28x squared y completely. Let's take a look at 64ab cubed. Let's factor, get the prime factorization of 64. Okay, first, okay, let's get 2 factors of 64. 2 factors of 64 are 8 times 8, and simply write out 8, a and b cubed on the other side. Okay, we know that 8 is not prime, so we continue factoring 8. 2 factors of 8 are 2 and 4, 2 and 4. We know that 2 is prime, so we bring down the 2. 4 is not, so we continue bringing down, factoring 4 to become 2 and 2, and do the same for this 4. And we simply bring down the a because there's only one a, and there are 3 b's. Okay, so we expand b cubed to become b times b times b, and this is how you factor 64ab cubed completely. Okay, and that is the end of our lesson, boys and girls. Thank you for listening and watching.